Hi, I'm Bob. Thank you so much for your patience and for doing the computer exercises with me. Today, let's finish the last 4 exercises for Chapter 16, Simultaneous Equations Models. Computer exercise 9 is about airfares. In part 1, a simple demand function for airline seats on routes in the United States is as follows. If this is truly a demand function, what should be the sign of alpha 1? Alpha 1 should be negative because higher airfare results in fewer passengers, other things equal. In part 2, estimate the equation from part 1 by OLS. What is the estimated price elasticity? We use the keep command to keep data for the year 1997. The OLS estimated price elasticity is minus 0.39. It implies that the demand for airline seats drops by 3.9% as the airfares increase by 10%, holding distance fixed. In part 3, consider the variables concentration, which is a measure of market concentration. Explain in words what we must assume to treat concentration as exogenous in the demand equation. The variable concentration should not be correlated with the error term μ1 in the model. In other words, concentration should not directly affect the demand for airlines or indirectly affect the demand through any channels other than the airfares. Under this assumption, the concentration is exogenous in the demand equation. In part 4, we assume concentration is exogenous to the demand equation, estimate the reduced form for log fare, and confirm that concentration has a positive partial effect on log fare. We regress the log fare on concentration and the other 2 exogenous explanatory variables, log distance and its square term. It is the reduced form equation for log fare. The OLS estimate of the coefficient on concentration is 0.40. We can use the summarize command to find information about the concentration variable. The standard deviation of concentration is about 0.2. The OLS estimate implies that a 1 standard deviation increase in the concentration leads to a 7.8% increase in airfares. The F statistic for the concentration significance is 39.67. It's high enough to satisfy the instrument relevance requirement. In part 5, we estimate the demand function using IV. Now, what is the estimated price elasticity of demand? How does it compare with the OLS estimate? Using concentration as an instrumental variable for airfare, the 2-stage least squares estimate of the price elasticity of demand is minus 1.174, implying that the demand for airline seats drops about 12% as the airfares increase by 10% after holding distance fixed and alleviating endogeneity by IV. As usual, we compared OLS and the 2-stage least squares estimates in a table using the estab command. We changed the significance levels for the stars and put the standard errors in parentheses. We also specify the format of the estimates. We find that the 2-stage least squares price elasticity of demand is much higher than the OLS elasticity of demand in size. The demand for airline seats is price elastic from the two-stage least squares point estimate, but unelastic from the OLS point estimate. The two-stage least squares 95% confidence interval is wider than the OLS confidence interval, but the former does not entirely contain the latter. They overlap partly. In Part 6, using the IV estimates, describe how demand for seats depends on route distance. The two-stage least squares estimates of the log distance and its square term are minus 2.176 and 0.187, respectively. The demand for airline seats decreases with distance first and then increases with distance. We can calculate the turning point. At the turning point, the first derivative of log passenger with respect to log distance equals 0. We use the estimates restore command to record the IV estimates. Then we compute the turning point distance. It is around 336 miles. Before that point, the demand for airline seats decreases with distance. After that point, the demand increases with distance, holding the airfare constant. About 11% of the observations are below the turning point distance in this sample. Let's solve computer exercise 10. Use the entire panel dataset in airfare for this exercise. The demand equation in a simultaneous equations unobserved effects model is as follows, where we absorb the distance variables into the individual fixed effects AI1. In Part 1, estimate the demand function using fixed effects and include year dummies to account for the different intercepts. What is the estimated elasticity? We estimate the demand function by individual fixed effects. We use the xtreg command in Stata to estimate the unobserved effects model. We use the FE option to specify the fixed effects time demilling method. We also include the year dummy variables in the model to account for the different intercepts. It can also be seen as the year fixed effects in the time dimension. So, the model is estimated with both the individual and the time fixed effects. In other words, we have controlled for both the time constant and the time varying unobserved factors. The estimated price elasticity of demand for airline seats is minus 1.16. It implies that the demand decreases by 1.16% if the price increases by 1%, other things equal. In Part 2, use fixed effects to estimate the reduced form equation for the log airfare. Perform the appropriate test to ensure concentration can be used as an IV for log airfare. The reduced form equation for log airfare is also known as the first stage regression. The fixed effects estimate for the concentration is 0.17. It is statistically significant at the 1% level, and the F statistic for its significance is 33, high enough to ensure a strong correlation with the endogenous variable of log airfare. It satisfies the instrument relevance requirement and can be a valid IV candidate. In part 3, we estimate the demand function using the fixed effects transformation along with IV, as in equation 16.42. What is the estimated elasticity? Is it statistically significant? We can combine the two methods in 2 steps. In the first step, we do the fixed effects time demilling transformation. That is, subtract the within individual sample mean from each observation. We use the by sort command in Stata to compute the sample averages of the variables within airline routes over time. Then we subtract the means from each observation. It is the fixed effects within transformation. The fixed effects AI1 will be removed after the transformation. In the second step, we estimate the transformed equation by pooled two-stage least squares, using the transformed concentration as an instrumental variable for the transformed log airfare. The estimated price elasticity of demand is minus 0.3, which is not statistically different from 0. We can also compare the 4 estimated elasticities by OLS, fixed effects, two-stage least squares, and the combination of fixed effects and two-stage least squares in the table. We include the distance variable in the OLS and two-stage least squares estimation. They have been absorbed in the individual fixed effects AI in the fixed effects estimation. We find that the fixed effects and the IV estimates of the price elasticity of demand are above 1 in absolute value. The insignificant estimate in the 4th column is due to little variation in variables after the fixed effects transformation and the IV transformation. Let's find answers to computer exercise 11. A common method for estimating angle curves is to model expenditure shares as a function of total expenditure and possibly demographic variables. A common specification has the form of the following, where S good is the fraction of spending on a particular good out of total expenditure, and L total expend is the log of total expenditure. The sign and magnitude of beta 1 are of interest across various expenditure categories. To account for the potential endogeneity of the log total expenditure, which can be viewed as an omitted variables problem or simultaneous equations problem, or both, the log of family income is often used as an instrumental variable. Let log income denote the log of family income. In part 1, use as food the share of spending on food as the dependent variable. What is the range of the values of as food? Are you surprised that there were no zeros? We use the summarize command in Stata to obtain information on the variable. The range of the share of spending on food is from 0.0571 to 0.789. There is no zero because food is a basic necessity. In part 2, we estimate the equation by OLS and report the coefficient on log of total expenditure. beta 1 hat, along with its heteroscedasticity robust standard error. Interpret the result. We use the variance-covariance matrix option to specify the heteroscedasticity robust standard errors. The OLS estimate of beta 1 hat is minus 0.15, which is statistically significant at the 1% level. It implies that as the total expenditure increases by 10%, the share of the expenditure on food decreases by 0.015 or 1.5 percentage points, holding age and the number of kids constant. Impact 3. Using log income as an IV for log total expenditure, estimate the reduced form equation for log total expenditure. Be sure to include age and kids. Assuming log income is exogenous in 16.43, is log income a valid IV for log total expenditure? In the first stage regression, we regress the endogenous variable log total expenditure on the excluded instrumental variable log income and the other two exogenous variables in the model. The OLS estimate of the coefficient on log income is 0.48. The F statistic is 281. It is much higher than the rule of thumb for the weak instrument 10. The endogenous variable is sufficiently correlated with the IV. The instrument relevance requirement is satisfied. Assuming that the instrument exogeneity requirement is also met, the log income is a valid IV for the log total expenditure. In Part 4, we estimate 16.43 by instrumental variables. How does beta 1 by IV compare with beta 1 by OLS? What about the robust 95% confidence intervals? We use the ivregress two-stage least squares command in Stata to estimate the model. We add the first option to report the first stage regression, and the variance-covariance matrix option to specify the heteroscedasticity robust standard errors. We compare the estimates in a table. The two-stage least squares estimate of beta 1 is minus 0.160. It is not very different from the OLS estimate. The robust 95% confidence interval is from minus 0.185 to minus 0.135. It is wider than the OLS confidence interval. In Part 5, use the test in section 15.5 to test the null hypothesis that the log total expenditure is exogenous in 16.43. Be sure to report and interpret the p-value. Are there any over-identifying restrictions to test? The endogeneity test can be performed after the two-stage least squares estimation. We type estat endogenous and find that we could not reject the null hypothesis that the log total expenditure is exogenous. The p-value is 0.25. We can also do the endogeneity test manually. It reaches the same result. The two-stage least squares estimation is not needed. There is only one excluded exogenous variable and one possibly endogenous variable, so there's no over-identifying restriction. In Part 6, substitute S alcohol for S food in 16.43 and estimate the equation by OLS and two-stage least squares. Now What do you find for the coefficients on the log total expenditure? We use the share of expenditure on alcohol as the outcome variable and estimate the model by OLS and two-stage least squares again. The estimates are listed in the table. The OLS and the two-stage least squares estimates of beta 1 are similar. The endogeneity test shows that we could not reject the null hypothesis that the log total expenditure is exogenous. OLS is an appropriate measure. We find positive coefficients on the total expenditure in the alcohol equation here, while the coefficients are negative in the food equation. Let's solve the last computer exercise for this chapter. Refer to example 16.8. In the dataset, variables beginning with G are growth rates from one year to the next, obtained as the changes in the natural log. Variables beginning with C are changes in levels from one year to the next. In part 1, estimate the equation by OLS. Remember to include year dummies for 1981 through 1993. Here are the OLS estimates. In part 2, estimate the reduced form equation for the growth rate of the prison population, where final 1 and final 2 are the instruments. Gamma 1 and gamma 2 are both negative. The two instrumental variables are individually significant at the 1% level. The F statistic for their joint significance is 8.56. They are jointly significant at the 1% level, but slightly lower than 10, the recommended rule of thumb for weak instruments. In part 3, obtain the two-stage least squares estimates of the equation in part 1, using final 1 and final 2 as instruments for the growth rate of the prison population. The two-stage least squares estimates are as follows. The two-stage least squares estimate of alpha 1 is larger than the OLS estimate in size. The OLS estimate is biased because of the simultaneous causality between the prison population and the crime rate. The OLS estimate is upward biased. Since the estimate is negative, it is biased towards 0. The OLS underestimates the prisoner's deterrent effect on the crime rate. In part 4, we use the cluster option in Stata to compute standard errors robust to heteroscedasticity and serial correlation for the two-stage least squares estimate. The robust standard error for alpha 1 hat is smaller than the usual standard error. In part 5, we estimate the reduced form in part 2 using the differences delta final 1 and delta final 2 as the instruments. Do delta alpha 1 and delta alpha 2 seem like sufficiently strong instruments for the growth rate of the prison population? In particular, do you prefer using the differences or levels as IVs? The reduced form equation using the differences as instrumental variables gives insignificant estimates for the instruments. The F statistic is tiny too. They do not satisfy the instrument relevance requirement. we prefer using the levels as the IVs. Thank you so much for doing the computer exercises with me for chapter 16 in the past few days. See you soon in the next chapter. Thank you for watching this video and subscribing to my YouTube channel. See you next time.